start up in about 5 seconds. I think that means let's start talking. Let's get the conversations rolling. Okay, welcome back everybody. I want to kick off with exam scores today. So I've graded your exams, so I'll hand these back to you at the end. If you guys want to work out solutions or anything like that, we can do that after class. Back in my office, we can do it. Thursday review session would be a good time to go through that stuff. Most of you guys were, well, I shouldn't say most of you. Quite a few of you were confused on the Bayesian question. No big surprise. So how do you do the normal analysis in a regression context? That problem is in the book a little bit further down in chapter 7. It's on Wikipedia, but probably not in the context of the regression problem that I set up. So saying that, all of the technical nuances are exactly the same as doing inference on a mean and a normal model. Those of you that know how to do that know that that's true, and those of you that missed that question a little bit are not sure how to do it still. A lot of you knew that the conjugate prior would be normal, the analysis would be normal, but couldn't figure out the parameters. So I graded that pretty easily for you guys. I'm happy to go through the solution of that problem. If it piques your interest, that's the whole goal. A good researcher might have been able to find the solution to that. A slightly perturbed solution and be able to doctor it up so it looks like the solution to the exam. And I think a lot of you did that. And that's good. So I probably wouldn't have asked that question had it been in class. So I'll give you these back in a moment, but we have to at least contextualize what does it all mean when you see your score. So let's go through some scores. I've loaded up scores. I've got them all into some vector called scores. I'm not going to show you all the numbers, but since you're all statisticians, what would you like to see?
Median?
Maybe the mean, right? It's like everybody always wants to see the mean. Let's go for the mean. Mean scores. Let me just ask a question. Why do you always like to see the mean?
100.
What's that?
100.
Well, it won't be 100. Like, that would be a little easy on the scoring. But why do you guys always ask for the mean?
To see where we stand compared to the
Right, but why not some other number? You're used to it. You're just used to it. That's all. That's the reason. You're used to it. Your third grade teachers taught you to think that way. So there are other numbers out there. We'll be talking about them in follow-up lectures. Mean, 95. Sorry. You know, I did go pretty easy on this. A lot of you had trouble with the question about is Fisher a frequentist or a Bayesian? Is Bayes a frequentist or a Bayesian? I had a couple good answers in here. Some spectacularly good answers. And then I had answers that were like frequentist, neither, both, who knows. So Danielle's like, yeah, I didn't spend any time on that. I just threw something out. If you just threw something out to me and I didn't like your answer, I'd mark you off -2. I've given that point total a total of 5, and I don't think I'd mark anybody off more than 2 points. So if I did that to you, take it with a grain of salt. It will make no impact in your whole entire life. If it does make an impact in your grade in this class, come and see me and I'll show you that it didn't make any impact. So it's just kind of a reminder. I'll read a couple solutions real quickly. Some people put a great deal of thought into this and some people put no thought into it. Some people said, well, Bayes is a Bayesian because his name is Bayes. That's not a reason. So the rule is attributed to Bayes. What we're doing is attributed to Bayes, but Bayes didn't say to do what we do. So I'll just point that out. Bayes passed away stating a correct probability rule. So he didn't say how to be a Bayesian. Laplace said something about all of that. And so Fisher was not necessarily a frequentist. It wasn't clear half the time what Fisher was doing. So Fisher did have fiducial stats. That's certainly not frequentist. Some people say, well, he came up with maximum likelihood estimators, which is fascinating because likelihood functions aren't frequentist in their nature. And maximum likelihood estimates maybe asymptotically have good frequentist properties in most cases, but for any given sample size, they maybe don't. There's no guarantee. So just because you do things that you think are frequentist, you have to think about what is the frequentist problem that you're guaranteeing. I'll pull my screen down just because I can't see anything with it. So I kind of like this answer. In general, R.A. Fisher is neither a Bayesian nor a frequentist. Yeah, that's kind of true. So, as Professor Bradley Efron once said, Fisher's theories are a collection of extremely shrewd compromises between Bayesian and frequentist ideas. It's kind of true. So, and even Fisher later on goes on to agree with that, but you will find far more quotes attributed to Fisher that are against that idea, that are contradictory. Say that, there's time. People change their minds. They say different things over time. It's common sense that frequentists and Bayesians mainly differ in several ways. I'll choose 3 aspects to illustrate how Fisher stands in the middle. I love it. Thank you. So, really like this answer. And they go through. So, to sum up, we cannot say Fisher was and so they talk about fiducial stats. They talk about some things that were frequentist. I love this paragraph. This answer is basically the reading of R.A. Fisher in the 21st Century by Professor Bradley Efron. It is a nice paper. So almost a citation. So this is just a midterm. You don't have to be perfectly clear about your citations. But if you do summarize somebody's idea, you have to put it in quotes. If you quote them, I would say this is a good paraphrasing, so no quotes necessary. Attribute the ideas. Part B was Thomas Bayes a Bayesian or a frequentist. If we're taking modern statistics context, Thomas Bayes again was neither a Bayesian nor a frequentist. His most famous contribution is the special case of what is now called Bayes' theorem. And so whoever wrote this agrees with me, but these aren't exactly my ideas from lecture. So they're getting it from somewhere else. It solved the inverse probability problem for parameters and blah, 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 blah. But ultimately, Bayes didn't say likelihood times prior and do something with that. Didn't construct all the decision theory. Just said what Bayes' theorem is. Didn't say likelihood times prior. So the likelihood function and the way we use it is the controversial thing, perhaps. So saying that, it's not that controversial anymore, because we can always check and validate how well methods work. This reading was a note of the Wikipedia page, and there's an attribution there. I like that. Here's even a slightly better answer. Was R.A. Fisher a Bayesian or a frequentist? So R.A. Fisher was a frequentist, and he has made major contributions to the frequentist method. Fisher popularized significance testing. However, there appears to be some differences between his earlier practices and his later opinions. In 1959, Fisher produced a new, more positive reading of Bayes, for he had found something to admire in what Bayes actually published, exclamation point. Somebody feels strongly. The change came about in a roundabout way as Fisher persuaded himself that he was repeating what Bayes has done 2 centuries earlier. Fisher may have started everything in a frequentist way, but he found that Bayes' theorem was reasonable and he used some of them without consciousness. So it's hard to say whether Fisher is a frequentist or a Bayesian. There is a problem with this paragraph that it does say Fisher's a frequentist, and then at the end it says Fisher was neither a frequentist nor a Bayesian. So somebody's playing the middle by playing both sides. And so that is an extremely well-written paragraph. I will ask the writer of this to come and speak to me because they didn't attribute it to anybody. So that's okay. We cannot do that in our professional careers though. So if you do write something that is a straight quote, you have to write down who wrote it. I will always know. So that's one of my great powers. I always know things. Still a wonderful sentiment. Now I'll show you the paper that this comes from. So it's worth reading for all of us. So I'll take this as a positive message, but if you do ever lift a sentence from somebody, it will end your career as a statistician if you do not put it in quotes and tell me where it came from. So in class, we can get away with this one time. I still like that this person came up with a reading and did some research. Just tell us what you did. That's what we're doing here, is we're attributing and then extending. So was Thomas Bayes a Bayesian or a frequentist? This one says Thomas Bayes was a frequentist, and we call him a frequentist since Bayesian came a long time after his death. Not exactly, but Bayes wasn't thinking this, so he's doing probability here. So use frequentist techniques. Bayes was neither a Bayesian nor a frequentist, and Fisher was wildly inconsistent. Fisher also came up with a lot of great things for us. So the paper that all this came from, and I'll post this to the Slack page. Aldrich wrote this, 2008 Bayesian Analysis. I've read this paper before. It's pretty good. So Ronald Fisher believed that the theory of inverse probability is founded upon an error and must be wholly rejected. So Fisher did say things like this. It's kind of interesting if you read through all this paper, what Fisher thought. He's all over the place. This note describes how Fisher divided responsibility for the error between Bayes and Laplace. Bayes he admired for formulating the problem. Somebody had mentioned to me, Fisher admired Bayes. Well, show me. How do you know that? You know? So maybe there is a statement out there. So how do we know what Fisher was thinking? So, but Fisher did think that Bayes was doing real mathematics and think that Laplace misinterpreted what he said. Maybe not misinterpreted, probably reinterpreted. And so Fisher for a long time was working with likelihood functions, but then he would admonish them sometimes. So he was a moody guy. So couldn't figure out what he meant. Laplace he blamed for promulgating the theory, and that's a good word for you, and for distorting the concept of probability to accommodate the theory. At the end of his life, Fisher added a refinement. In the essay Bayes, it anticipated one Fisher's own fiducial arguments. So Fisher changes his mind. I'll post this for you, but I get a little bit tired when people are like, I'm a frequentist or I'm a Bayesian. You know, it's know what you're saying, know why you're saying it, in what way are you being a Bayesian, in which way are you being a frequentist, so on and so forth. People say, well, I like Fisher, he's a smart guy, so I'm going to do exactly what Fisher was, and Fisher was a frequentist. Fisher didn't know he was. So, and Bayes hadn't thought about it yet. So, anyway, the answer is a little bit more complicated. Anyway, attribute your answers if you do use direct quotes. If you do this in a paper or something like this or at a conference, your career ends. So if you do it right here, we'll have a nice conversation about the whole thing. I do appreciate people going through literature. I like that answer a lot more than the, I don't know, you know, or the frequentist, or Bayes frequentist. So I like reasons. It's okay if you don't want to humor me and you didn't want to collect 2 points. So it will make no difference. But anyway, the answers are starting to converge what these concepts are. So I'd say things like the EM algorithm, is it Bayes or is it frequentist? It certainly feels like Bayes on the E step, and it might have some frequentist properties from the M step. So it's kind of a mincing of 2 philosophies. So it's neither, it's both. It might be frequentist, but we'd have to check whether or not the intervals or that likelihood estimator, what properties it has on average compared to the truth. We'll study that as we delve into chapter 7. So 95 was the mean. Any other numbers people want to see?
Median.
Median. Yeah, okay. I like medians too. Median scores. So 96, right about the same. Anything else?
Mode.
Mode.
Box plots.
99. I get a lot of 99s. Anything else? That's all you need to know, right?
Standard deviation.
Standard deviation, yeah. So, don't tell me what the variance is. Tell me what, put it on a scale I understand. Scores. Anything else? Killing it. How many dimensions are we living in right here? It's 1. What do you really want to see? You want to see the histogram. So show me the distribution of everything. Don't want all these summaries. You could just plot this for somebody. Then you might ask for the other stuff. So that started to say something right there. I would say basically everybody did really well. I would say everybody's on track to do fine in this class. There is no problem here. I kind of consider all that stuff on the right-hand side minus one score over to the left, and that person did fine too. Probably needs to clean it up. So probably not great to get a 75 on a take-home, but most of those things, when I looked at all the scores, they were mild bleedings of points. A couple points maybe could be cleared up, but when I look at the exam, I know that all of those points that I scored off, whoever missed those points is going to be able to clear up those ideas in their head. And that's what the exam is all about. So a lot of people are stacked to the right. It's a totally different distribution than I would normally have in class. So when you get your scores back, just read through it. Think about the stuff that you missed. Think about why I maybe marked you off points. If you want to discuss it with me, let's discuss it. I did go through it twice just to make sure I was being reasonably fair about everything and consistent, but I might be off by a point here and there. So your friend maybe got one extra point than you did on something. I wouldn't worry about it. But if you are worried about it, come and see me with that as well. So those are the scores. I'll hand those back at the end of class. Let's say everybody's doing pretty well. Think about how long it took you to do the exam where you were stuck, if you could have figured out how to not be stuck. But I think in the sense that everybody has limited time and wanted to get everything turned in, everybody did a really good job. We'll go through the Bayes problem maybe at next review session if you'd like. And if you can't make that, we can do it at my office hours every day after class. I usually reserve about an hour. If you guys swing by. Okay, back to EM. Yes.
For the next exam, is that going to be given next week? Or
Yeah.
Okay.
I'm gonna hand it out next week. It's gonna be take home.
Okay.
What exactly is the due date? Don't know. So I'll think about it. Do I want to give you 3 days or a week? Who knows? So it depends on how many questions I decide to ask you. So I know you want to plan, but there's a little bit of variability in your life right now. It'll be reasonable. It'll be equitable. You'll have time to do it. Really, I want to just provoke your thinking about questions. Okay, we're still on schedule for an in-class final. Okay, back to EM. We ran this code last time. I was talking about a 2-component mixture model. I knew the variances and I ran this code and everything seemed to do well. So I ended up sampling a number of data points. It's a large number of data points. And so everything worked pretty well when the modes were separated pretty reasonably. I'll just remind you what I did. So EM. Basically, I simulated data, 2 well-separated modes, and then I just iterated over the EM algorithm. My true parameters are 10.5 and 2, and my true mixture weights were 0.3 and 0.7. So it does pretty good. And if I run it again, the answer might switch a little bit. It might switch the positions of the modes. It might change a little bit. There's local maximum. So what you want to do when you do this is run it over and over and over again, check your likelihood functions, and make sure you store the one that's the biggest. Saying that, in one run of this algorithm, it does okay. If I took data away from you, it might not do quite as well. Let's just see that. N is equal to 10. EM example, there's my data. I run everything, it ran really quickly because my likelihood evaluations were almost instantaneous. And the answer did pretty good. Still good. 10 data points, I can kind of tell you what the model was. I'm off here, 0.4, 0.6, but I'm in the ballpark. So it did an okay job. So even with 10 data points, not so bad. That's because these modes are really well separated. So as you end up making the modes closer to each other, I'll even give you a little bit more data in here, just so we can resolve everything, see what it is. I'll say maybe this is 4.5. Standard error is 1. Those are reasonably close to each other. Here's what that two-modal distribution looks like. It looks heavily skewed. You can't really see that there's two modes in there precisely. So it doesn't look normal either. And the answer isn't that bad. 4.5 and 2. So it's kind of amazing. But this code is able to discern what my driving model parameters were. So again, I'll remind us what they were. 2 and 4.5. True p is 0.7, the other 1 minus p is 0.3. So this is what I was saying, like you can use these mixture models to come up with a lot of things. This looks like a skewed distribution and not a two-modal thing. But I'm still able to figure out from this data what the parameters are reasonably close. If I push these modes right on top of each other, we have no chance of being able to discern everything. So let me do that just real quickly. Let's make both modes 2. The variances are both 1. So I've got a two-component model where the modes completely overlap each other. This is called an unidentifiable system. You can't tell me what the parameters were. You can't tell me what the probabilities were anyway. Let's just see what happens. Run this thing. My mu's are converging to 2, and those p's are something. 0.645, 0.35. Let's rerun it. My modes are 2. That makes sense. And my probabilities completely changed. Because you can't discern them. They could have been any number. And so there's actually a ridge in that likelihood function for what the pi's are. And so it could have been anything between 0 and 1, and you would have fit the data just as well. So as we become more and more unidentified, the problem gets harder and harder. As we move into high dimension, the problem gets harder and harder as well. That's what you'll study on your simulation assignment, how well it works in general. So I'm going to leave that here, and I want to go into a proof that the EM algorithm works. So again, there's just 2 steps for EM. So EM is just this. I've got some function, maybe I'm thinking that is likelihood. Could be some other function, it just needs to be positive for all this stuff to work. But I'm going to write down Q, theta, is equal to expectation of the log of whatever function I'm playing around with. I'm going to just write it down like this. Since I'm a statistician and this is the most common usage, this is maybe a likelihood function. Let me be more general. I'll just say F. And then I'll say usually this is a likelihood. Of course, in my Bayesian mindset, if I'm going to integrate over a likelihood function, I think what I just said is I used the uniform prior. So the flat prior across the whole space. Apparently, if you would have told Fisher that when he was a young man, he would have been upset with you. And if you told Fisher that when he was an older man, retired, he would have said, I guess. So begrudgingly. But we don't really know exactly what Fisher was thinking all through his life. All we know is what he said. So this is going to be given theta t. And then I'll just write down that we always have the data. I'll just write this down that that's data. Everything's conditional on data. And then we optimize this thing. So theta t plus 1, my update is an arg maximum over theta, where I've conditioned on my last iteration. So this is an iterative algorithm, and it converges in on the maximum value of theta, but in the sense that I've averaged away psi, the missing thing. So in the context of our mixture model, those are our labels. We don't get to see them. We just get to see the histogram. I want to infer what all those parameters are that are driving the model, so I'm going to average away all of my mixture labels. So I'm doing an on-average analysis. Feels a little Bayesian in that step, and this one feels a little bit maximizing likelihood. So maybe that has a frequentist property, and oftentimes it does. We'll say something more about that when we get to this part of the lecture. So we're going to prove that this solution, so t is going to go from 1 to cap t, is t goes to infinity, theta t, or I'll say t goes from 1 to cap t. This goes to theta hat, where this theta hat is going to be the R maximizer of some function, f theta psi, given data, d psi, integrating over all of psi. So I'm going to R maximize that over theta. So I'll just write this down. This is the R maximizer over theta of this function right here, f theta. I'm going to just drop my notation where I'm conditioning on the data and just expect you to remember everything's conditioned on data. If there's ever a step in your life where you didn't condition on data, back up. So unless you're just being totally reckless, maybe a little exploratory. Okay. So this is just the integral of everything. It's not quite obvious that maximizing this margin right here is the same as maximizing Q. They don't look the same. There's kind of an advantage of working with Q. It's this iterative process. So I'm kind of getting closer and closer to theta. So I'm breaking the whole problem up into these little maximization problems. And so if you know anything about fixed point theory, we're setting up a fixed point in the thing where everything is convergent. I'm not going to say too much about that. I'll say it's kind of a good idea, instead of just maximizing an entire function all at once, maybe it's a good idea to slowly iterate and maximize so that we hone in on the answer. Because that's an easier thing to do, and if you've ever studied anything like Newton's method, you get that you're kind of walking towards something. You can usually do that fast. So let me just write out what f theta is. So I'm going to write down that my conditional distribution, f psi, given theta, is going to be equal to the joint distribution. I'll put it on the left side. The joint given the margin. Let me just be real clear, since I changed the notation ever so slightly. This right here, what I really mean is f psi given theta and my data. I've just suppressed my data notation. This right here is f theta and psi given my data. And this right here is f theta given my data. This is f theta given data. All I've done is drop the d everywhere. Everything is conditioned on d everywhere. So I'm just going to rearrange this and write down f theta is going to be equal to the joint divided by the conditional. And if I saw this, I'd probably think that's weird. There's a psi on the left hand, there's a psi on the right hand side, and there's no psi on the left hand side. If you know about conditional distributions, you know that they're always proportional to the joint distribution. So that slice cutting through something that we call conditional distribution looks just like the joint distribution shape. It's just rescaled so that it adds to 1. And so it wouldn't surprise me if you told me these are distributions or likelihood functions that the sides were canceling. I would understand that instantaneously. So I'm just going to write down I'll just write this down. Log of f theta is equal to the logarithm of the conditional minus the logarithm of still would have been true. So that they would be proportional to each other. But this is what I mean. I was just trying to rearrange this equation. That probably makes everybody feel just a little bit better. So this is going to be the log of the joint minus the log of the conditional. If I want to optimize f theta, I can optimize logarithm of f theta, no problem. It's a monotonic function, so we've been doing that since we learned about calculus and we were optimizing. Go ahead and take a log. It's usually a pretty good idea if you're working in the exponential family, take a log, because it linearizes everything. So that's kind of nice. But without any loss of generality, maximizing the logarithm of the function is maximizing the function itself. And so what we do in EM, I'll just point out, is we take an expectation. I'm going to take an expectation on everything. It's going to be 2 expectations that I'm going to write down. So this is going to be the logarithm of f theta. If I do something to the left-hand side of the equation, I do the same thing to the right-hand side of the equation, I don't mess anything up. Log joint log conditional. I'll just remind you that's a negative sign right there. That will be important to us in a second. So there's a specific expectation that I have in mind to take with respect to psi given theta t. Psi given theta t. Psi given theta t. So I've treated both sides the same, so everything is still equal to each other. I just want to point out, there's no psi over here. So this thing that I'm taking an expectation over with respect to psi is just a thing in the first place. So I didn't change anything. So this is just the logarithm of f theta. So the thing that I want to maximize on the left-hand side is equal to these 2 pieces right here. And if we go over and we look at the EM algorithm, this thing, the way that I'm writing it down, is just f theta psi. I've just dropped my data notation. Everything's conditional on data. So even when I take this expectation, I'm conditioning on data. So I've just suppressed the notation is all. So this Q function is sitting right here. This one. The difference between these 2 things. So this is Q. And this is some other function. Subtract this other thing. I'm going to call it S. Just some other function. It doesn't have a sign there, I've integrated it away to get its average. And so EM is not maximizing that, it's maximizing this thing. Only this first point. What I have to convince you is that doesn't matter. This is not in the book, so it's also not too difficult. So what's the nice thing? Here's kind of the insight, I think. I know some of the guys that have worked on this have the early papers on it. And I usually say something like, well, it's just kind of obvious that you would condition on where you were last time. Let's try to set up an iterative algorithm. It seemed like the right thing to do. I know a little bit about fixed point theory, so this was obvious to condition on where I was last time. And if you're a maximizer, maybe that's obvious to you. So to do that. So I want to set up something that converges. I'm going to just take this function right here. I'm going to grab this answer, and I'm going to plug it in here. get a new argmax, pump it in here, keep iterating, it should converge. So, and if you've ever seen anything like Gauss-Seidel, those sort of algorithms, you'll be familiar with that. That's kind of what they're doing. Newton's algorithm is kind of like this iterative algorithm. So there's a little bit of insight on why you would condition on this, but I would say maybe it's the obvious choice if you're setting up an iterative algorithm. Average away the thing you don't know. So here's a fact. S theta given theta t is a decreasing function. We'll prove that. So I just want to make a point that if I started moving this function, whether or not I make this function go up or down, this function's always going down. So what I mean in one dimension is this looks something like this. I've got a theta t. This is going to be my space for theta, s theta. So at this point right here, this function s goes down. It doesn't go up. Those are just flat things at most. If it looks like my function went up for a second, let's make it look like it never does. It just goes down. If you want this to look a little bit smoother so you can remember it, because it probably isn't this bumpy, it does something like this. So if I move away from theta t, the function decreases in value. So no matter what I do to theta, this part goes down. This part might go up or it might go down. And so if I iterate over q and I increase it, this is automatically going down. So if I play around with q and I maximize it and I take the value of theta, it maximizes this on the next step, like step 2 of the EM algorithm. Whatever I'd be plugging into s would make this decrease. This is a negative sign. So I'd be subtracting something that's going down. So what I just said is it is sufficient to optimize Q to optimize F. So no matter what I do, this function goes down. We proved that. So it's going down, getting smaller and smaller and smaller, and I'm subtracting that thing off. If I were adding right here and it was getting smaller, well, I'd be adding some small amount of value, and that function could jump up. But because I'm subtracting whatever this is, right here, it always goes down. So if I can prove that statement right here, I will have proved it is sufficient to optimize Q, to optimize cap F. And the little bit of insight in all of this is we've also formed an iterative algorithm simultaneously by conditioning on the previous draw. So that's kind of cool. I bet that was exciting when people noticed this for the first time, that you could do this, and it basically tells you how to proceed algorithmically. Kind of like that. So let's just prove that. So we'll prove. So I'm just going to write down real quickly something that I know. So I'm going to integrate over f psi given theta t d psi. Now let's just temporarily, so that we don't have to deal with arbitrary normalizing constants, we already know that if I multiply this by some positive scale factor, I could maximizing a positive scale factor right here would preserve the maximum. Put it in the same place and just make it higher. So what I want to do is I want to consider this a distribution, f. If it's some positive function like likelihood function, and that function is positive function that we're playing around with as statisticians, then I could normalize it. and make it a probability distribution. It would preserve the maximum. So without loss of generality, I'm going to assume this is a probability distribution. It doesn't really change the answer. I like thinking about it that way anyway. So that's usually what I'm doing. So I've scaled it so that it's a probability distribution. And I'm integrating over the entirety of psi. Does anybody know what this is? This integral? If that were a probability distribution, what would this integral be? 1. So that would be 1. If I took the logarithm of that, what would the answer to this equation be? 0. So pretty easy so far. So that's 0. Okay. So I'm just going to mess around with this for a minute. This is going to be the logarithm of the integral of f psi given theta t divided by f psi given theta t plus 1 times f psi given theta t plus 1. All I did was multiply by a funny form of 1. That's it. So just a funny form of 1 right here. I'll just point out that this equation right here that I just wrote down, I can interpret this in a particular way. I can write this down as this is the logarithm of the expectation of whatever this thing is. So that's the logarithm of this expectation. I'm multiplying something by a density function. When I see that, I think that's an expectation, that's an average. This is an average of this function right here with respect to that distribution. So if you want to be specific, I'd write down this is psi given theta t plus 1. That's what that is. This right here is not just a monotonic function, it's concave as well. Concave up, concave down, we'd have to think about that. I always call these things convex functions. So I know an inequality that deals with these things. You guys know it too. Jensen's inequality says something about this. So Jensen's inequality relates the logarithm of the integral f psi given theta t over f psi given theta t plus 1 times f psi given theta t plus 1. I know that this has something to do with this function. So I'll just write again down this whole integral is just the expectation of f psi given theta t over f psi given theta t plus 1. To finish this, I need to tell you what I'm integrating over, but you can see it right on the board. So this has something to do with this function. The logarithm of that. So I can relate this to the expectation of the logarithm of f psi given theta t over f psi given theta t plus 1. Somebody help me out. Which way does this inequality sign go? It's not equal because that's not a linear function. It's the only time these things are equal. This goes this way. So somebody can draw that picture pretty well in their head. So Hopefully I've shown you how to do that, so if you did get stuck, you'd be able to convince yourself that's the right direction. So this thing right here is going to be the integral of the logarithm. And I'm going to write this out into two pieces and just separate this. F psi given theta t, d psi minus integral logarithm f psi given theta t plus 1 d psi. I missed my whole density function, didn't I? So times f psi given theta t plus 1 d psi minus integral logarithm psi f psi given theta t plus 1 let's get my density in there, psi given theta t plus 1. So that's what we have. So we just bounded something. This was equal to 0 when we started. So I'll just point out, this is S theta given theta t. This right here is S. I'll say this is t right here. Sorry, this is t plus 1. I must look real quickly. This is t. Yeah, oh, okay, that's it. Yeah, my integral sign and my s's look the same. You're not the first one to tell me. So, yeah, those are s's. So, let me just do this real quick. Sorry, you guys, I made my error. I fixed this up. Great minds at Virginia Tech have helped me to think through this problem. And we've got everything worked out so we can prove what we wanted to show. That result over there. So the correct way to do this was to integrate over theta t plus 1. If we do that, everything works out great. So same thing, multiply by some version of 1. Jensen's inequality gives me the inequality facing that direction. I move the logarithm inwards. I expand everything in terms of the logarithm. And then I identify that this function right here is S of theta t plus 1, conditional on theta t. And this is S at theta t given theta t plus 1. So these are S functions. That's an integral solve. At the end of the day, I just rearrange this, and I pull this to the other side of the 0. And this is our result. So all we said is S is a decreasing function. It's also positive, it's decreasing. And so we're always subtracting something off. So we have an algorithm for optimizing F by doing this iteration. So we're relieved because we can solve this problem in a Bayes, non-Bayes sort of compromising fashion. So now everybody's perfectly dissatisfied with it. Or maybe it even works. On your homework, you'll demonstrate how well this works. There's other solutions to the problem. That's all I have for now. Have a great weekend, you guys.